sparking depends on the position of the brushes. This line through points of zero generated EMF is called the neutral plane. Placing the brushes in this neutral plane reduces the tendency for sparking between brushes and commutator, because during the time a brush is touching both commutator segments, there is no difference in potential between these segments. Theoretically, no sparking should occur at the commutator brushes when they are placed in this position. But the current flowing in the armature loops or coils sets up a magnetic field of its own. This magnetic field interacts with the main magnetic field and distorts it. The distortion causes a shift in the neutral plane and sparking at the brushes. The effect is called armature reaction. Sparking may cause severe interference in nearby electronic equipment. There are two ways of maintaining the neutral plane in its correct position and thus avoiding sparking. It may be done by the adjustment of the brush position. The brushes are adjusted to lie in the adjusted neutral plane. The other way of maintaining the neutral plane is by adding interpoles to the generator field. These interpoles are small magnets placed between the poles of the main field magnets. The interpole fields oppose the fields created by armature reaction. The neutral plane is moved back toward the correct position. In addition, to further counteract armature reaction, windings called compensating windings are sometimes placed in the main pole faces. The current in these windings is armature current flowing in opposite direction to the current in the armature conductors. Magnetic fields in DC generators may be produced by electromagnets or permanent magnets. Permanent magnets are used in relatively small devices like a field telephone ringing generator. In larger generators, the field is created by electromagnets. The field winding used in this DC generator can be represented by a symbol. The symbol is that of an iron core inductor. Current to excite the field windings can be supplied from an external source. In that case, the generator is classified as separately excited. A small part of the generator's own output can also do the exciting. In that case, it will be a self-excited generator. Self-excited generators must be initially magnetized. The residual magnetism in the core of the field winding provides enough magnetism to begin generator action. The field coil winding may be connected in several ways. This is a series wound generator, which means the field coil is in series with the armature. Because of this series arrangement, it has poor voltage regulation. The reason for this can be demonstrated in the following manner. Additional load will cause more current to flow in the field coil. Increase in field strength increases voltage. Increase in voltage causes more current to flow. This continuing action stops only when the core is saturated. When the load is increased, the voltage will increase. When the load decreases, voltage will decrease. Voltage regulation in the series wound generator, therefore, is very poor. When instead of in series, the field winding is connected in parallel with the armature and the load, we have a shunt wound generator. Now the field current is independent of the load current. Therefore, an increase in armature current will not cause an increase in the voltage output. Voltage regulation here is greatly improved. In shunt wound generators, therefore, changing load causes relatively small change in voltage output. By changing the armature winding, a compound wound generator results, which combines the best features of both types, the series and the shunt wound generator. When windings are arranged so that magnetic fields oppose each other, it becomes in effect a series generator. This is used only where constant current is the prime requirement, such as in arc welding. By changing the magnetic polarity of one of the fields, the field windings aid one another. As a result, this compound wound generator has good voltage and fair current regulation. A graphic representation of generator output characteristics with terminal voltage plotted vertically and armature current horizontally would look something like this. As we have seen, in the output of the series wound generator, voltage regulation is very poor. In parallel or shunt wound generators, the voltage regulation is fairly good, but current regulation is poor. Compound wound generators offer a flat compounded output that is normally most desirable. It combines the good features of both the shunt and series wound generators and provides stable voltage output under changing loads. As we have seen in our analysis of the DC generator, its primary function is the conversion of mechanical energy to electrical energy. If we now reverse the procedure and connect an electrical power source to the generator, we have a DC motor instead of a DC generator. Motor action can be illustrated by attaching a power source to a conductor which is inside a magnetic field. The electric current creates polarity in the conductor. The south pole of the magnet attracts the north pole of the conductor and repels the south pole. The north pole of the magnet attracts the south pole of the conductor and repels the north pole. This creates movement depending on the direction of the steady magnetic field. The movement also depends on the direction of the current flow through the wire. By changing the polarity of the battery, the conductor now moves in the opposite direction. To see what really happens, let's go to a drawing again. Here, a conductor is suspended in a magnetic field. Current flow from a power source creates its own magnetic field in and around the conductor. This field around the conductor reacts with a main magnetic field to cause motion of the conductor either out of the field or into it. The arrow point indicates the direction of the current flow in the conductor. In this case, the flow is toward us. The field of the conductor has the same direction as the main field above the conductor and the opposite direction of the field below the conductor. These two magnetic forces added together distort the lines of the main field upward. The field above the conductor is thus made stronger and the field below the conductor is made weaker. So the conductor moves down. Conversely, when current flows in the opposite direction, that is to say, away from us, the field of the conductor opposes the main field above the conductor. This aids the main field below the conductor, distorting the lines down. The field below the conductor is thus made stronger, while the field above the conductor is made relatively weaker. This forces the conductor to move up. With this basic principle of motor action understood, we can now examine the DC motor.